They want us to partly look at what we looked at at the other time, and then progress. Just to be familiar with the pairing groups. We had looked at this, and I want us to be familiar with it because it's very crucial going forward. So first of all, again, I begin by reminding us the importance of this concept of pairing groups, and by saying that it's very important in cryptography, particularly in construction of zero-knowledge proofs and other cryptographic protocols. Now, again, I have to remind us what pairing groups are. We go back to the definition of pairing, and we said pairing, bilinear pairing is just a mapping group 1, the product of group 1 and group 2 to another group. So it's mapping elements of group 1 cross group 2 to another group. This is bilinear pairing. Of course, it fulfills other conditions, which we looked at, binarity and so on. Now, this group is what we call the target group. Target group. So members, we shall be mapping to members of this target group. And these two groups, these are what we call the pairing groups. These are the pairing groups. So you pick one element here. Of course, by these groups, we mean elements of an elliptic curve. Those are points on the elliptic curve. Remember, the elliptic curve comprises of points. The elliptic curve comprises of points. So these points form, together with the identity. This is element at infinity. So these points together with this element, they form a group. And this group would have subgroups, several subgroups. So we just picked one subgroup and another subgroup from this group. Of course, subgroups form groups. Subgroups form groups. So a subgroup is just a group again. So you pick one subgroup and another subgroup. And then from this subgroup, pick one element. Let me say P, and another element from here. Let me say Q. So we want to map the elements, these elements, to the target group. So by doing this, by definition, we are getting some constant like R, and another constant, let me say P, such that this will be the same as PQ AB. So just by definition, we are getting those two constants AB. That's the definition of this bilinear pairing. Bilinearity, that's what I mean by bilinearity. Now, so this is what we are getting. So you pick one element here, one point, another point. So then there is an algorithm. This algorithm, of course, will on its own compute A and B, such that this map E would map this element to this. So that is what we'll be looking at. But of course, by pairing group, we are just looking at this subgroup and this subgroup. So what we want is how do we come up with a code that will give us this subgroup and give us this subgroup. And then later on, we shall look at now, once you have this subgroup and this subgroup, and you pick an element P and another element Q from this group. Now, how can you find an element in this group? So we'll be doing that when we'll be looking at Weyl pairing. And of course, we'll look at other types of pairing. Weyl pairing is just one of them. There are several other types of pairing. So we are picking, we shall be picking later on, shall be picking a point here. Let me say P another point Q from this other group. Then we do some whale pairing, and whale pairing will not be obtaining A, B, of course, shall be coming up with an algorithm. That algorithm on its own can identify A and B, and then give you an element from the target group. Yeah, but that one is later. So today, again, we look at the pairing groups. The pairing groups, how to obtain the pairing groups. And of course, we now know what pairing groups are. Now, last time we looked at that concept, and so we're just emphasizing what is happening there. These two groups, these three groups, that what I must emphasize that they are of the same order. These three groups must be of the same order. So group one is a subgroup. I've said it's a subgroup. A subgroup is just a group. If this is of group order R, by order we mean number of elements in the set. So if this set has R elements, this must also have R elements, and this must also have R elements. The target group must also have R elements. So they must be of the same order for you to do any pairing. So this group must be of the same order with this, then you can conduct pairing on them. And of course, when you do that pairing, they'll result to another group of the equivalent order. So the order again will be the same. Now, the other point that I need to emphasize is that group one and group two are both additive. They are both additive groups. They are both additive groups. But now, when you multiply the element there and the element there, when you do that mapping, they'll result to a multiplicative group. So this one is a multiplicative group. By multiplicative group, I mean the identity element here will be 1. And here, of course, will be 0. So when you're, that is for the purposes of writing the code. For the purposes of writing the code, the identity element here is 1, and the identity element here is 0, 0. But of course, the identity element is always, we always denote it by element at infinity. Is an element at infinity. But that when you're writing the code, this additive group, the element at infinity should be put at 0, 0. That is x, xy should be 0, 0. Xy should be 0, 0. And for this one, then maybe you can say 1, 1, 1. Or just 1, 0, 0 when you're using polynomial. But the identity here should be 1 when you're writing for purposes of writing the code. Because when you're writing the code, you are telling this and map this to this multiplicative group. So then you are telling it what the identity element should be in the multiplicative group, and what the identity element should be should look like in the additive groups. So that is enough about the two groups. Before we go into how do you then determine, so we're still emphasizing a few things on that. Now, here is just an emphasis of the definition of bilinear pairing. Bilinearity, what bilinearity means, what non-degeneracy means. And degeneracy is very important. It's very important when you're writing that code, just to ensure that not all your elements will be mapped to the identity element. Non-identity elements should not be mapped to identity. So if P is not an identity element, if it's not a point at infinity, you don't expect it, this map, to map P to identity. You should not map it to identity. So if Q is not identity element, this map should not map it to identity. That's what we mean by non-degeneracy. That is the importance of non-degeneracy. That's why I've said this ensures that the pairing function does not map all pairs to identity. That's one importance of that. Then, of course, the other property is that there must be an efficient algorithm that can compute the pairing. That algorithm must exist. Now, let's go to, these are just where the importance of these pairing groups. This one you can go through them. So I want us to go straight to how do we get this group and how do we get this group. Of course, these groups, we shall be using what we call the Frobenius endomorphism. But this one, I'll emphasize it mostly when I'm doing this group 2, when I'm finding group 2. Now, when I'm finding group 1, I can use the same knowledge we used of R-torsion groups. R-torsion groups, where R is a divisor, and a divisor of the order. So if the order is 9, the divisor of the order is 3. So we can have 3 torsion group. If the divisor is 20, if the order is 20, the order of the group, then the divisors are 2 and 5. The divisors of this, which the prime divisors, not just divisor, but the prime divisors of this order. One of them is 2, 2 can divide that, and 5 can also divide that. But for the sake of this calculation, when you're calculating G1, you find 5 torsion. So you use the largest divisor. And the essence of this is just again for security reasons. Of course, the largest divisor will give you the higher embedding degree, which will then again result into more security for your system. So for the purposes of calculating G1, you are using the highest divisor to get your R torsion group. Now for this group 2, we shall emphasize a Frobenius or Frobenius endomorphism. And again, I'll explain what that is and how to arrive at group 2 using a code. Today, I'll emphasize group 2. I'll look at the code for group 2. Last time, I looked at the code of group 1, and group 2, I was not able to find it how I had saved it, but today I have it. Now, so what is Frobenius endomorphism? What does it say? This is just the function for Frobenius endomorphism, and says that this pi would map the elliptic curve to the same elliptic curve. So what this actually means is that while you're doing this, the elliptic curve does not change. It remains because, for instance, supposing your original field was this, and now you are doing in the field the extension, let me say that. But if your elliptic curve was this, so you're considering the same elliptic curve, whether here or here, you're considering the same elliptic curve. So the elliptic curve remains the same. The elliptic curve remains the same in both cases. It does not change. But what it says, that a point xy would then be mapped to a point, or becomes x raised to p, y raised to p, where p is the characteristic of the field. Like in this case, the characteristic is Q. If I'm talking of F5, the characteristic is 5. So this point, if I had a point xy, this xy should become x raised to 5 in this case, then y raised to 5. But the identity element will just be identity. But if this function would map the identity to identity, but it maps this point to this point. But the elliptic curve remains the same. So that is what the morphism means. And we'll look at calculations to see how it works. And then proceed and find group 2 and use this Frobenius endomorphism. Now let's look at an example straight away. The example is, how do you compute G1 and G2? How do you determine, or the same as determine G1 and G2 if you're given the elliptic curve x cubed, that 1 is 1 and b is also 1. And then the field is F5, where 5 is our characteristic. Now to get G1 is very easy. We had done this before. For you to get G1, the first thing you do is to find the embedding factor. And then you can come up with the extension after you gotten the embedding factor, it will assist to get the full torsion group. But this we had already done. We had already done that. And when we did that, we found that this elliptic curve, first of all, it has 9 points. This elliptic curve has 9 points. So its order is 9. And the prime divisor of the order is 3. So we can find 3 torsion group. So 3 torsion group would then be our G1. But how do you find 3 torsion group? To find 3 torsion group, the first thing you do is you can find full 3 torsion. This is one way. If you want to do it manually, this is how you do it. You find full 3 torsion, and then you realize that the 3 torsion is just a subgroup. This is the group, and then the subgroup becomes this. By 3 torsion, what do we mean? 3 torsion, these are elements which, when added 3 times, would give the identity. When added 3 times, will give the identity. So once you have these elements, once you have the full group, you iterate the elements here to check which ones, when added 3 times, gives the identity element. So you go through each of the elements. That is the longest way. But now we had a code for doing this, we had a code for doing that. So the code will just be testing the elements of the group and finding out which points, when added 3 times, gives you the identity. Now, so that is, but let's go this longer way and see. The longer way says, after you found the order of the group and the divisor, you find the embedding degree. What is embedding degree? Embedding degree K is the smallest element which makes R to divide this, the right-hand side. The smallest positive integer that will make this divisible by R. R in our case is 3. So what will make 3 to divide 5 raised to K minus 1? There are several elements that can make this equation, that can make the right-hand side divisible by 3. But the least of them all is what we want. And the least of them all is 2. 5 raised to 2 is 25, minus 1 will be 24. So 24 will be, 3 can divide it. 3 can divide. So the least positive integer that can make this divisible by 3 is 2. And therefore 2 is the embedding degree. So once you have the embedding degree, you can easily now calculate the 3 torsion, because you will now be extending it in the field F52, where 2 is the embedding degree that we now have. You're now extending it. So you now find points here, points of this. You see, this one has only 9 points. This one has only 9 points, but this one has more than 9 points. Part of those more than 9 points is the 9 points which were here. The 9 points which were here are here. And then on top of this, we have several other points. So these 9 points plus several extra points will now form the full 3 torsion group. So in our case, I think it had 25 elements. But it had 9 elements. 3 raised to 2. It had 9 elements. No, not 9. 5 raised to 2. Now 5 raised to 2 are elements. But now, out of these elements, we want to form points. And I think we got, I don't remember very well, but I think we had 17 points. 17 points. This one had 17 points. Now, of course, we have 25 elements, but now you're trying to see what I mean by 25 elements are these. Elements like 1, 2, 3, and I'm talking of mod 5. So when I talk of mod 5, I have this 1, 2, 3, 4, 5 elements. Mod 5, I have 1, 2, 3, 4, 5 elements. But mod 5 raised to have 25 elements. Now, out of this, when you combine these elements, suppose I have that and I have 0, 1, 2, 3, 4, 5. So you know how we normally combine them. You can get 0, 0, but we are asking ourselves, does it form a point? Does it form a point on the elliptic curve? Then we have 0, no, let me say 1, 0. And then we ask ourselves, does it 1, 0 form a point? What about 2, 0? So out of these 25, out of these elements, there are some that when combined will not form a point. But now, of all those elements, there are those only 17 points can be formed. Only 17, around 17, I think. I don't remember when we did that, but I think there were around 17 points when you combine the elements. The elements that would form points that are on the elliptic curve. Now, once you have those 17 elements, you now want to check which ones are 3 torsion. 3 torsion. So it means you're checking which of those points, when added 3 times, will give you the identity. When added 3 times, will give you the identity element. So that's what you'll then be checking. Now, you can do that using Rust code later on. Earlier on, we had done and we found that the 3 torsion would have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 points. That means when I'm talking of 5 torsion, I'm talking of 25 points. 5 torsion. By the way, our interest here, we don't have 5 torsion. Here we have only 3 torsion. Because it's only 3 that it divides 9. It's only 3 that divides 9. Now, so when you use your Rust code, gives you these points, and we had done that. We had done that earlier on. Only part of these points will give us G1. G1 will have only 3 points because it's 3. Okay, what is it? It's 3 torsion. It's 3 torsion. This is full 3 torsion. This is full 3 torsion, but now you're talking of 3 torsion. 3 torsion will have only 3 points. So these are the points which, when added 3 times, gives the identity. When added 3 times, gives the identity. So when you add this 3 times, gives the identity. So that means when you're writing your code, you are putting there the formulas for adding the points. And we have all those formulas. We have the formula for getting the slope. When you're adding points, you see you have to use the slope. Now, if the points are different, then the slope is changing y, changing y over changing x. y1 minus y2 minus y1 all over x2 minus x1. This gives you the slope. Then you can calculate x3. The x coordinate of the new point is x3. Then you can also calculate y3. x3, the formula, I think it was this, gradient minus x1 minus x2. Gradient square minus x1 minus x2. So this one, you must put it in your code. You must put that in your code. Let me just, yes, so you put that in your code. So I'm just checking my code. X3 is lambda times lambda minus x1 minus x2. So you must put in your code. Then you will now calculate y3. Y3 will be lambda times the difference of x1 and x3, then minus y1. So x3 has just been obtained here. So again, you're putting in your code the formula for calculating y3. So once you have x1, x2, x3, and y3, you have a new point now. That's a new point. So all these formulas, you must put them in your code. I had said you must put a code for doing the gradient. And that's what I just want to show you. If the points are different, if the points are different, the gradient should be change in y over change in x. Change in y over change in x. But normally, it's very hard to do this. So what we normally do, this is the same as change in y, then times the inverse. Of course, this dividing by a half is if I have, let me say 3 over half, or 3 over 2, the same as 3 times the inverse of 2. 3 over 2 is the same as 3 times the inverse of 2. So that's what I'm doing. Instead of writing this, I can say times the inverse of the denominator. The inverse of the denominator. And that's what I've written here. So I've said, let the numerator be this. Let the numerator be y2 minus y1. And then let the denominator be this mod inverse. So that now you will multiply the numerator times the denominator. So the denominator, you've already defined it as mod inverse of x1 minus x2. Of course, you are dividing by the mod. Whatever the number, whatever the multiplication is going above, you are dividing by the mod, m. But now the result that you get, which is the inverse of the denominator, you'll multiply that inverse by the numerator to give you the gradient. So that is how you find the gradient. If 2 points are not the same, if 2 points are not the same, so you need to understand the code, how the code is working here, what is happening. So after you've gotten the gradient, now you get x3 and y3. There are cases when the points are equal, so the gradient is obtained in a different way. The gradient is obtained in a different way. So if x1 equals to x2, x1 is equals to x2, and y1 is equals to y2. So you are talking about a point like P is 9, 4, and Q is 9, 4. So you can see x1 and x2 are equal, y2 and y1 are equal. So in such a case, how do you find the gradient? How do you find the gradient? The gradient is given by, normally it's supposed to be 3x1 square, then the result you add a. Then you divide by the denominator, which is 2y1. 2y1. So of course, we've already said we can never divide in this kind of calculations. We can never divide. So what we will then be doing, we'll just take the numerator, then multiply the inverse of the denominator times the inverse of the denominator. So that's, when you check, you will see that is what is happening here. So the numerator, you call it 3 times x1 times x1, then plus a. Of course, the number will be, at some point, will be greater than our mod. So you reduce it. You reduce it by your mod. Then the denominator, let us call it mod inverse. Mod inverse of 2y1. Mod inverse of 2y1. So once you get that denominator, you now multiply it by the numerator. And that gives you the gradient, our lambda. So that's how you get lambda. When you are doubling a point, the same point you are doubling it. Once you have this gradient, again, getting y1 and y2, no, y3 and y and x3 is the same way. You get it the same way. X3 and y3. So that's how you see when you're writing that code, you want your code to give you G1 or 3 torsion. You want it to give you 3 torsion. So you must tell it at some point you'll be adding points, and so this is how you'll be adding those points. So you're telling it, for instance, if you're adding a point P and Q, and if P is at infinity, then if P is at infinity and you're adding it to Q, the result should be Q. The result should be Q. And if it's Q that is at infinity, and you're adding it to P, the result should be P. That's what we're telling it. And then you're telling it that if the x value of P, the x value of P equals the x value of Q, if the x value of P equals the x value of Q, and if the y value of P is not equal to the y value of Q, or if the y value of P is 0, and then the result will be at infinity. So what it means, whenever you're adding 2 points, if the x values are equal, irrespective of what is here, if the x values, once the x values are equal, it means these points are on the same vertical line. The result should be point at infinity. The result should be point at infinity. That's what we are telling it. We're telling it that if you find that while you're summing up, you find that the x values are equal, then the result should be point at infinity. Now, just looking at the code, we have not looked at this code. I want to look at it so that I will go look at the one for obtaining G2. Now, you're telling it how to implement a point at infinity. How to implement a point at infinity. So this one is beginning by determining is at infinity. The point is at infinity. Let me say, like, supposing the result, I've added this 9, 0, and I've added to 9, 4. The result is at infinity. So the result of the point at infinity. But now, how does a point at infinity look like? A point at infinity, this function tells us at infinity is a point that looks like this, 0, 0. So it's just defining how a point at infinity looks like. But this other one is telling us a point is at infinity. It's just telling us that this point that we've obtained is at infinity. I think you're getting that point. So this function here is just to implement point at infinity and how the point at infinity looks like. So that is the first function. Then this other function is doing the mod inverse. Is finding the mod inverse. This part you looked at it several times. You are beginning by initializing these mutable values, initializing t to be 0, then initialize new t to be 1, initialize r to be m, and initialize new r to be the remainder of a on division by m. Then after initializing that, you enter some loop, and it says, the loop says, and you can see where I'm reading, it's saying while the new R is not equal to 0, while the new R is not equal to 0, you remain inside this loop and do these calculations. The only time you exit these calculations is when the new R is 0. When the new R becomes 0, you exit the loop. But while it's not 0, you continue doing this. So what are you doing here? What you are doing here, you are letting the quotient to be R, and so on, and so on. Now, so once you exit, when you find that if R happens to be greater than 1 after all these calculations, and you've reached the end, and R is greater than 1, then there's a panic. There's a panic. And the panic means that the number you are dealing with has no inverse. The number that the error you are dealing with has no inverse. For it to have an inverse, okay, you have done this, and you found that the new R is 0. Because that is the only time you're exiting. That's the only time you're exiting the loop. You exited the loop, you found that the new R is 0. New R is 0. But now check the R at that point. R at that point, at the point when new R is 0, what is R? If at that point R is still greater than 0, greater than 1. If at that point R is still greater than 1, then it means there will be that number has no inverse. That number has no inverse. Now you proceed and check T, the value of T. Supposing there's an inverse, check T. Of course, T is supposed to be that inverse. But now, if it's less than 0, you must add M to it so that you now get T. If it's less than 0, you add M to it. But if it's not less than 0, there's no problem. So you don't add M to it. You're only adding M if it's less than 0 to make it positive. Because it's supposed to be positive. The inverse is supposed to be positive. It's not supposed to be a negative number. It's not supposed to be a negative number. It's supposed to be positive. Then there's a point, this one you had already explained. You had already explained how to add. It's just your summing, how you're summing. So you explained that. So you proceed to scalar multiplication. Now, scalar multiplication is what we want. Is what we want here, because what are we doing at this point? We had already said that three torsion group or point, three torsion point is a point of the group which, when multiplied by 3, or when added to itself 3 times, when added to itself 3 times, it must give you the identity, the point at identity. Above there, we've already defined what a point at identity should look like. We've already defined what a point at identity should look like. So you're telling this code to now be able to multiply points by scalars. So you want it to be in a position to multiply P by 3. And then when it multiplies by 3, if it gets this point at infinity, okay, that's what you want it. You want it if it can get this also at some point. So you want it, for instance, it will be doing this. For it to do 2P, it's not just multiplying 2 times P, it's just adding P to itself. It's adding P to itself. Where we have 3P, is not just multiplying 3 times P, it's doing this. So it's not doing it on its own. It's using this function above. The function above, we've just been telling it how to add. How to add if a point is added to itself. We have given it a formula for getting the gradient. You have given it a formula for getting the gradient, and you have told it how to do this gradient. You have told it how to do this gradient. Then after doing this gradient, you have told it how to get x3 and y3. If the points are different, like in this case, the points are different. Because in this case, this one was 2p. In this case, it's taking, this is the same as 2p plus p. So 2p plus p, these are two different points. And since these 2 points are different, you've already told it above that in such a case, find your gradient as y2 minus y1 over x2 minus x1. And of course, you have told it further that this will be the same as y2 minus y1 multiplied by the inverse of the denominator. You told it further that way. And then you have told it, after doing that, now find x3 and y3. And how are you doing that? You've told it that we'll find x3 as lambda square minus x1 minus x2. And you'll find y3 as lambda into x1 minus x3, then minus y1. We've already told it about there. So when you come to this scalar multiplication, you'll just be calling on those functions above, and the functions above are doing that for it. So it just says, let's find 3p, and the function above knows to do that. It requires p plus p, that's doubling. Then later on is 2p plus p, and you have 3p. Now let's look at what I wrote here. I've said a function for scalar multiplication of n mod p. No, okay, n and p. So where n here is the scalar. N is the scalar in our case 3, and p is the point. So let the result be the point at infinity. Initially. But now, so you initially, you let your result, the result for scalar multiplication, let it be a point at infinity. It will be changing. So when it adds now p plus p, the result will be 2p. So now it changes from infinity to 2p. Now, so you'll add, let mut addend be p, and let mut n be n. N is just, this one is just our scalar. But it will be changing. So while the scalar is greater than 0, while n is greater than 0, enter this loop. Now, if n and 1 are 1, if that result, if n is 1, then the result will be the elliptic add. It calls on this. So it calls on the result, calls on this function, which we have above, to add. If n is 1, so you're just adding p once. So of course, what I've just said is what this code is doing here is just doing what we've talked about here. P, if you're not adding it to anything, and then if you're adding it to itself, then if you're adding it 3 times, But again, it's not doing it on its own. It's calling on the elliptic add function, which we have here, elliptic add. So the elliptic add function, we've already told it how to add these numbers. We've already told it. So it's just calling on that, and it's calling on it. So if it's one adding p, just p, not adding it to anything. So it's just one p. Let this one do it. Then it does. One p is just p. What about 2p? What about 3p? So this order. The elliptic add does it. The elliptic add function does it. Now, as I said, these codes we've done them several times. So if you have one code, you just play with it and come up with other codes. Now, this part is just to determine if the point is on the curve. Is on curve. You see, after this summation, you just want to be sure that the point, the result you've gotten here is a true result. For it to be true, you've got a point. Can you be sure that that point is on the curve? How do you tell if a point is on the curve? If p is at infinity, then you return true, though it means it's okay. It's okay, this point. Okay, we know that a point at infinity is never on the curve, so we have no problem with that. So if the result here was at infinity, we have no problem with that. So it returns true. But now, if the point is not at infinity, if p is not at infinity, this one we must do some work. We must do some work, and the work we do it is to use the curve. Use the curve. So how do you use the curve? Take the x value. Take the x value of q bit. Take the x value of q bit. This is what I'm doing here. Yeah, I'm cubing it. And then the result that you get, add a times x. A times x, add that. Then add b, and call this the right-hand side. The right-hand side. Then what about the left-hand side? Take the y value that you got, then square it. Square it. If it's bigger than mod, just reduce it. Square it and call it the left-hand side. If these two are equal, the point is on the curve. The point is on the curve if they're equal. If they're not, then there must be a panic that this point is not on this curve. So that's what is happening at this point. Now we have done scalar multiplication above. We have done scalar multiplication for those points. Now pick those ones that gave you 3p is infinity. Pick those ones. Above there, scalar multiplication, just multiplying. Just finding what 3p is, finding what 2p is, or what 4p is, or 5p is. Just doing scalar multiplication. But now this time what we want is those that when multiplied by 3, you say that. So just go back to scalar multiplication. You're calling on that function. That function, you are checking those that were giving you identity when multiplied by 3. So to do that, you're checking through all the x values and all the y values from 0 to m. So let point xy, now, so if the point xy is at infinity and then false. But if, so that one we don't check. That one is obvious. It's obvious that 3 times a point at infinity shall be a point at infinity. There's no problem there. But if the point is not at infinity and is on the curve, if it's not at infinity and is on the curve, this one, we check r times that p. We check r times that p by using scalar multiplication function above. Scalar multiplication function above, just call on it scalar multiplication function. So the scalar multiplication function is supposed to tell us the result of multiplying r and p. It's supposed to tell us. And it says, if that result is at infinity, so again, you're calling on the function is at infinity. You're calling on the function is at infinity. Of course, this function, scalar multiplication, is just giving the result of multiplying 3 times p. It's just giving the result. So it's telling you the result is 0, 0, for instance. Or the result is 9, 0. The result is 9, 0, for instance. Now, after you have this point 9, 0, 9, 0. So now colon is at infinity. And you're asking it to tell you if this point is at infinity. You're asking it to tell you that point is at infinity. If 9, 0 is at infinity. If 9, 0 is not at infinity, you have nothing to push. If it's not at infinity. But if it's at infinity, you're pushing it inside this empty vector. Pushing it there. If it's at infinity. So again, you can see it's not that it's doing this, it's just asking other functions above. And these other functions have been told to how to understand if a point is at infinity. So it's at infinity, has been told that if a point is at 0, 0, that point is at infinity. That point is at infinity. But if it's not at 0, 0, it's not at infinity. It's not an infinity point. So that one has already been defined at this point. And that's why we began implementation of a point at infinity. So we've already told it is at infinity. We told it that a point is at infinity if the x value is 0 and the y value is 0. So when you ask it to check 9, 0, just compares this to this and it determines that the x value is not 0. So this one is not at infinity. But if you give it this compares to that and it tells you that this point is at infinity. Now, so that is how we are doing this torsion thing. And this is the function that is doing that. So we are pushing every point that is a torsion point to the empty vector there. Then, of course, you have the main function. And the main function is just assisting us, asking for this. We want to print for us the torsion points. Of course, we are giving it the parameters of our elliptic curve. We're telling it that the elliptic curve, the x value, the x coefficient is A1 and B is 1, and our gradient, not gradient, our mode is 5 in this case, and our R is 3 in this case. So we wanted to give us torsion points, but it cannot do that without the help of R torsion points. Find R torsion points. Find R torsion points is this function here. find R torsion points. And find R torsion points has been told how to find the torsion points. It knows how to do that. It knows that at some point to be calling on this function. At another point, to be calling on this function. Another point, to be calling on this function before it comes up with the torsion points. So then it calls on those functions. Those functions also know how to perform their role. They have already been told how to do that. Now, so it calls on the find R torsion points. It just gives it gives that function the parameters. It gives that function, it gives this R, it gives it A, gives it B and M, and then it tells it, give me the R torsion points. And the R torsion points proceeds the way it has been told to do. Now, once the R torsion points replies, it replies with the torsion points, this will then print torsion points on that curve. Now it says for point in the torsion point, you enter this loop. If point is at infinity, I ask it to print. Ask it to print if it's a point at infinity. Else, also print that. Also print these points that are not at infinity. If they're not at infinity, so what I'm talking about is here. The results here. The results here. I've told it for the results that have come from this, those which are at infinity, just write for me that the point is at infinity. For those that are coming, you see this one, find R torsion points will have to respond. It will have to respond. It will have to give this, the points which when added 3 times gave you point at infinity. So I'm just telling it that of those points that have come from above, if you find that one of the points is at infinity, just write point at infinity. But if you find that these other points, like P, for example, you find is 3, 4, just write 3, 4, 3, 4. If you find 4, 2, just write 4, 2. So that's what I've told it. So let me just share the code, and then we'll look at the other code for finding G2. So I've avoided looking at the manual calculation because we have done that. Manual calculation. So the torsion, R torsion code, the code for finding R torsion points is the one I've been explaining. Is here. I've already explained the whole of it, beginning from function at infinity and so on. Find the mod inverse, I've explained that. And so let's come here and insert our values. A value is 1, B value is 1, and then our mod was 5, and our R was 3. Then we know that it must give us 3 points. It must give us 3 points because we're talking of 3 torsion. 3 torsion. So 3 torsion means to get 3 coordinates. Yeah, it has done that. It has done that. I'm just referring here. Just referring the last. This is what it has given us. 3 torsion points are here. Now, at this point, I had asked it that if a point is at infinity, just print for me point at infinity. And you can see that there was a point at infinity has written it here. It has written here point at infinity. And for points that are not infinity, I've told it But if the points are not infinity, just give me the point. Give me the x value and the y value inside the bracket. And so it has done that at that point and this point. So these 3 points are those which, when added 3 times, you get point at infinity. And therefore, together they form G1, or group G1. Together they form that. Good. That's how we find group G1. And I've explained the code. Now I want us to slightly manually look at how to find G2, then use that manual calculation to write the code, which I already written. I already have it. So I'll share the code. G2, I'd already defined the Frobenius endomorphism. It's the one that will be helping us to find G2, and particularly this this map here. That the map will be mapping xy to x raised to p, y raised to p, where p is the mod, where p is that mod, or the characteristic, where p is the characteristic. So I'm looking at this question, and now how do we find it? Proceeding with this question we were looking at, how do we find G2? Remember, G2 must also be a subgroup of this group. This is the full torsion group. This is the full torsion group. So this full torsion group, we've already identified G1. We've already identified G1 as 3. G1 is this. One we just used our code. Our code has already given us G1. This, and this. It's a subgroup of that. Now what we now want is G2. So G2, by definition of that Frobenius endomorphism, are points here, which x raised to p, our p in this case is 5, x raised to 5, y raised to 5, give us 5p. So that is what you give your code. That's what you give your code. You're telling your code that if you find a point like this point, 1t, try take 1, raise it to 5, and take t, raise it to 5. Then do the calculation. See whether the result is the same as 5 multiplied by 1t. If the result is the same, then this point 1t is one of the points of G2 group. Is one of the points of G2 group. Remember, G2 group must also have 3 points. Must also have 3 points. Because G1 already has 3 points, and of course, these 3 points are coming from the fact that we're talking about 3 torsion. 3 torsion. It already has 3 points. So G2 must also have 3 points. And those points are those which will fulfill this condition. They are part of these points. So which one of them? When raised to x value is raised to 5 and y value is raised to 5, the result will be the same as 5 multiplied by 5. So those points then will qualify. So this is just a formula giving that code. It's not the only formula. It's not the only formula. But from this, You can now notice that there are various things you're supposed to do here. How do you multiply? How do you do this? You must tell this your code what polynomial you are using. For instance, in this case, our polynomial is y squared plus 2. In our workings, we've been using this t squared plus 2. Is our polynomial. So you're telling it anything above t squared, anything t squared and above must be reduced. How do you reduce it? T squared is equals to -2. Is equals to -2, which is 3 mod 5. So anything more t squared and above, it's 3. Anything t squared and above is 3. Like, for instance, when you're talking about this, raise it to 5, you have 1 raised to 5, and then t raised to 5. So 1 raised to 5 is 1. That one has no problem. But t raised to 5 is t raised to 2 times t raised to 2 times t. But t raised to 2 is 3. And t raised to 2 is another 3. So you're talking of 1, then 3 times 3 times t, which is 9t. But we are talking of mod 5. So this is 1 4t. So we just found that 1 raised to 5, t raised to 5 is the same as 1 4t. 1 4t. What about 5t? What about 5 raised to? What about 1t? Will it also give us this? So this means you're adding 1t plus 1t 5 times. 5 times. So that means you're giving this code a method for doing summation. Just like we explained about the other code. You're giving this one that when you get 1t plus 1t, these are at the same point. Find a gradient by 3x1 square plus a over 2y. You're telling it that. Because you're dealing with the same point, find gradient as 3x squared plus a over 2y. You're telling it that. And then after that, after finding the gradient, find x3 this way. Find x3 this way. Then find y3, give it a formula. Now it has already done x1t plus 1t. Now it has 1t. What it has already obtained here. Let me say now this is the same as, let me assume that x3 was 5 and y3 is 6. Now these 5, 6, add it to 1t. Add it to 1t to get 3 times that. So all these formulas you need to give your code. So it must do that until 5 times. And then you must now give it a code, now a function that will now be equating the left side and the right side if they're equal. And then it tells you that this point qualifies as a part of that group, as a member of that group. Let me share the code so that you look at it. Last time I didn't share this code because I could not see how I saved it. Now this is the code that will be doing that. Now we had looked at a similar code when we are doing extension fields. A similar code. So I just looked at that code and I just changed a few things. Of course, the only place I changed was the endomorphism, the Frobenius endomorphism, where I'm giving it the condition for doing that. But you can see the other parts of the code are the same. For instance, this part is the part for summation, point add function. I'm telling it, if you're adding P to Q, and if P is at infinity, then the result is Q. And if P is the one that is, if Q is the one that is infinity, the result is P. And if X, okay, so let X1 and Y1 be this point, and X2 and that will be that point. Now, what I want now to do, I want to find the gradient if, for instance, okay, this one I already explained. If X1 is equal to X2 and Y1 is not X2, it's not Y2, Y1 is not equal to Y2, then the point, that point, it means that the points are on the same vertical line. So the result will be a point at infinity. But if that is not the case, how do you find the gradient therefore? How do you find the gradient? So you're showing it how to find the gradient. And remember this part, where you have the denominator, you are multiplying the numerator by the inverse. So I just only changed the language here, but it's the same thing. Only changing the language, but it's the same thing. What about for point addition, where the points are different? How do you find the gradient? It should be changing y by changing x. So I've just said y2 minus y1. Then the denominator x2 minus x1. Just changing language, but it's the same thing. And again, once you have y2 minus y1 as the numerator and x2 minus x1 as the denominator, you cannot do that. What you can do is you can multiply the numerator by the denominator, the inverse of the denominator. You can only do that. Then after that, find the x3 and the y3 value. Then the previous code also had this code for scalar multiplication, and I explained it. That part for scalar multiplication. Then now, the only new thing is now when we are applying the Frobenius endomorphism. Now, so we have libraries that define Frobenius endomorphism. So you only actually don't need to put a formula here. You don't need to put it, that it must be x raised to 5, y raised to 5 should be equal to 5p. Short, not a must. There we already have libraries that define Frobenius endomorphism, and they'll just be doing that for you. They'll be doing that for you. You're not doing it from the scratch. Not doing it from the scratch. You're just calling on those libraries. Okay. Now, the other part is find G2 points. Find G2 points. So here is where you may now want to define what a G2 point is. So a G2 point would be, if you get G2 points, we'll be pushing them inside this empty vector. So what a G2 point will be a point of the full torsion group such that now we have the x cubed part. Because I'm looking at, okay, this is what I want. This is what I want. X raised to 5 times y raised to 5. No, x raised to 5, y raised to 5 should give me 5p. Just as the previous example. So this is what I'm then defining here. But the first part, this part is just a definition of the elliptic curve. It's just a definition of the elliptic curve where we have x cubed plus ax plus b. So I've said x cubed should be the same as this. Then after that, what will be the right-hand side? The right-hand side will be x cubed plus ax plus b. Then I'll be using this code now. I'll be now looking at this curve and checking if the point, first of all, is on the curve. After checking that, then I want to take the x value. I want to take the x value, and then this x value, raise it to 5. Of course, I'll call it Frobenius. You're calling on point Frobenius, and then 5 times p. 5 times p. So that means I'm multiplying that point 5 times. 5 times. Point multiply 5 times. And that gives me 5p. Now, if the Frobenius equals to 5p, it means that point is a point of the group G2, then you push it there. It's a point of G2, and then you push it there. So this is how we're getting those points. That's how you're getting those points. And then we have the main function and so on. Then, of course, you tell it what to print and so on. So let's just, I have not run this code, let me run it. Now, this point this curve, I've already said my R is 3. And we've already defined now, so when you run this, now it gave me, I began by asking for all the elements of the group. Then after that, the points on the elliptic curve. So, but what we're interested in, and then we have the full 3 torsion point, but that's not our interest. Our interest is group G2. Group G2. And this is a group that has points such that x raised to 5, y raised to 5 is 5p. And there are 3 points. There are 3 points under here. That's how you do it. So this is what I wanted us to actually look at. Once we have this, once we have a way of finding G2 and a way of finding G1, then we are able now to proceed to Weyl pairing. Okay, thank you. Yes, Kimani, you have a question?